In this second tutorial, we will begin to evaluate using sigma notation and to be able to write arithmetic series using sigma notation. So if you would turn over to this part of our notes, sigma notation. Sigma notation is a concise way to represent a sum. So really, whenever you see this sigma symbol, and that's this big capital E looking thing, that is representing a sum. That's what sigma notation is, summation notation. Okay, and don't worry if it looks like I'm starting to speak Greek to you, because, sigma is a Greek letter. Yeah, I thought that was funny too. Okay, so let's make sure we understand how to read this symbol, because if you don't know how to do that, then it's going to be tough to do. So you've got this sigma, that's the big capital E, that's the sigma symbol. You have a number underneath that symbol, you have a number above that symbol, and then you have an expression to the right of that symbol. So the first number that we deal with is this lower bound right here. That's what this is called, the lower bound. In this case, that's a 1. This is the first number to plug in. The first number to plug in. We're going to plug this number right into this expression, and that will give us our first term. So when I plug a 1 into 2n, 2 times 1, of course, is 2. And then I'm going to plug in every number from 1 to 10, and then I'm going to stop at the 10, because the 10 is the upper bound. 10 is the upper bound. This is the last number to plug in. So we're going to plug in the lower bound, and we're going to continue to plug it in all the way until we get to the last number. So we plugged in a 1. Next we'll plug in a 2. 2 times 2, of course, is 4. Next we'll plug in a 3 and get a 6. Plug in a 4, we'll get an 8. Plug in a 5, we'll get a 10. Plug in a 6, we'll get a 12. Plug in a 7. 2 times 7 is a 14. Plug in an 8, we get a 16. Plug in a 9, we get an 18. And finally, when we get to our upper bound, we plug in the 10 last, and that gives us our last number of 20. So instead of writing all of these numbers every single time, all 10, I believe it's 10 terms, we can write that sum using a very concise method called sigma notation. Now this sum ultimately is trying to add up to a certain number. If we added all of these numbers together, we would have 110. So we still need to be able to find the sum, but the first thing we need to do is be able to unlock what this symbol means. So let's look at example 6. It says to evaluate, and the word value is almost in that word. Evaluate means to find the number that it's equal to. So this time we have this expression 3k plus 2. We've changed our variable. K is equal to 2 is our lower bound. So we're going to plug the 2 in here first to get our first term. 3 times 2 is 6, plus 2 is 8. So that's my first term. I'm going to plug in a 3 and a 4 and a 5, and then the last number I'm going to use is the 6. So let's plug a 3. 3 times 3 is 9, plus 2 is 11. 3, what am I doing? I plugged in my 3. Let's plug in a 4. 3 times 4 is 12. 12 plus 2 is 14. I plugged in a 2, a 3, a 4. Let's plug in a 5. 3 times 5 is 15. Plus 2 is 17. Do you start to see a pattern here from 8 to 11 to 14 to 17? You see that this is arithmetic and that we are adding 3. Well, that's interesting that we're adding 3 because there's my coefficient of 3 right in my expression. If I go back to my previous example, I was adding 2 to get from term to term to term. That makes that arithmetic as well. And it's not a coincidence that the coefficient is a 2. In fact, whatever the coefficient in our expression is, that's what d will be, and that's what we'll be adding to get from term to term. So in this case, d was 3, so we must be adding 3. So 8 to 11 to 14 to 17. The next number should be 20. Let's confirm that by plugging in my upper bound. 6 times 3 is 18, and 18 plus 2 indeed is 20. So once I find all of my terms in my series, I'm going to add them all up, and I will get 70. So this is how we can unlock our sigma notation. Spill out all of the terms that it's equal to and add them all up. Now, if we had a bunch of terms, maybe we use one of our previous formulas to be able to evaluate the sum. But this was only 10 terms. 10 terms is not too bad, and I can add those up. This was only 5 terms, and I could add that up to 70. Let's look at our final example. Our final example is going to actually go backwards. I'm going to give you the series of numbers that are added up, and I'd like to write it backwards into sigma notation. So let's look at our first one. We have 5, 10, 15, 20, 25, 30, 35. You can see that the pattern is adding 5. So this is arithmetic. And that must mean that d is equal to 5. And it is helpful to know that because we just found out in the previous example that that value of d will be a coefficient in our expression. So let's write our sigma symbol. Now my sigma, it just kind of looks like that. The real sigma, I'll do it over here. I just don't usually take the time to write the entire thing. There it is. I just do a big E looking thing like that. It's fine. So I know that my expression is going to have a 5. Now I need to choose a variable, and I'll just choose n. Let's say n. So 5n has to be part of my expression. That doesn't necessarily mean that this is the expression, but I know that since d is 5, 5 times my variable will have to be part of my expression. Now, you could technically start with whatever lower bound you want, but I think that it makes the most sense to try to start with a 1 every time. And in fact, I can see that when I plug a 1 into this, I'm going to get my first term. And then if I plug a 2 in, I get my second term. And when I plug a 3, I get my third term, and so on and so forth. We need to know what the last number to plug in will be. Well, you can either see that it's 35 and realize that that would be 7, or you could just count your terms. 1, 2, 3, 4, 5, 6, 7. If you start with 1, then you would end with a 7. And we just did it. That is a sigma notation that expresses that sum. Let's look at our final example, example 7b. Let's look at this. We've got 7 to 10 to 13 to, it looks like there are some terms missing. I know that I'm going to end at 31, but there's some terms that are missing right here. That's what this little ... means. Okay, so it's arithmetic. I know this because I am adding 3 and then adding 3 again. So I know that in my sigma notation, I should have 3 times my variable, and I'll just choose n again. Now this time, if I start when n equals to 1, my first term, according to this expression, would be 3. But that's not correct because it's supposed to be 7. So what I can do to my expression is add 4 to it. I still like to keep my 1 as my lower bound, my first input. When I plug a 1 into here, 3 times 1, and then add 4, I will get my 7. Let me put this in parentheses because that's what we should do when we have a binomial. Let's see if this works for the second term. The second term would be found by plugging in a 2. So that means 3 times 2, which is 6, and then 6 plus 4, hey, that is correct. We get a 10. Maybe check one more time. Plug in a 3. 3 times 3 is 9, and 9 plus 4 is 13. So this starts to work. I see that. The question is, where do we stop? We don't have the luxury of being able to count all of our terms like we were able to do in part A because they were all there. We're missing some terms. I need to figure out what number to plug into this that would equal 31. Well, you can sort of see that as like an equation, I guess. 3n plus 4 equals 31. You could subtract the 4 and you'd be to 27, and then divide by 3 and you'd see that it's 9. What I'm doing is saying that this 31 is equal to 3n plus 4, and then solving this equation. And I get that n is equal to 9. That is my upper bound, so I can put that right in here, and I have my sigma notation. The other way you could do is you could keep listing the other numbers and get to 16, 19, 22, 25, 28, and then 31. Did I mess up there somewhere? Nope, that'll do it. So that's going backwards, and this is a skill that I know we should probably practice more in class. So thanks for watching this, and I will see you in class. Bye-bye.